Newton's legacy is a testament to the profound interplay between theory and practice, marking a turning point in the history of scientific thought. Born amidst the upheavals of the 17th century, he harnessed experimental insight, mathematical rigor, and creative intuition to redefine our understanding of nature's laws. His work transcends standard textbook paradigms, embedding deep technical insights that remain essential to experts and researchers. Today, we dissect his contributions with a focus on advanced topics, exploring the intricate mechanics behind his methods, using detailed numerical analyses and rigorous derivations that challenge even seasoned academics. Our journey begins by assessing the extraordinary breadth of Newton's mathematical innovations, particularly his development of what he termed fluxions, an early incarnation of calculus. We will delve into the complexities of his geometric interpretations and limiting processes, revealing the computational precision and elegance of his methods. Each discovery is tied not only to a historical context, but also to technical advancements that propelled subsequent research in fields such as differential geometry, numerical analysis, and applied physics. Next, we turn our attention to his experiments in optics, where Newton's methodological creativity shines through. His deconstruction of white light using prisms and the subsequent revelation of the color spectrum underpin modern optical physics and have inspired generations of experimental techniques. Finally, we explore his formulation of the universal law of gravitation, which integrates advanced mathematical tools with empirical astronomical observations to deliver a unified framework for celestial mechanics. This narrative is supported by reliable data, historical manuscripts, and analytical reconstructions, providing a fact-driven exploration that moves well beyond introductory explanations. In the following sections, we will present a rich, expert-level discussion designed to engage those who are well-versed in these technical realms, ensuring that every statement is grounded in precise numerical and analytical evidence. We begin now. Newton's foray into the domain of calculus represents one of the seminal breakthroughs in mathematical history. In the mid-1660s, while retreating from academic formalities during the Great Plague, Newton conceived a fresh approach to analyze continuous change. His notion of fluxions provided a geometric language that captured the behavior of varying quantities through limiting processes. By May 1665, Newton had established methods for computing the tangent to any continuous curve and precisely determined its curvature. These achievements were documented in manuscripts that underscored his acute understanding of infinitesimals and the power of geometric reasoning to solve complex problems. His work, titled De Analysi per Equationis Numero Terminorum Infinitus, circulated among his peers even before his formal publication. In correspondence with figures such as Isaac Barrow and John Collins, Newton demonstrated a command of series expansion, binomial generalization for arbitrary exponents, and techniques for solving nonlinear problems. His derivation and application of the generalized binomial theorem provided a robust framework for approximating functions and laid the groundwork for methods that would later be formalized in the modern development of power series. Such detailed manipulations of infinite series were not merely algebraic exercises, but instrumental in bridging the gap between geometry and analysis. Newton's method of successive approximations, now widely known as Newton's method, revolutionized numerical analysis by offering a systematic procedure for finding roots of functions. This method, which iteratively refines estimates, is a predecessor to numerous algorithms used in computational mathematics today. Furthermore, his work on finite differences led to techniques that underpin modern interpolation theory. Although his notation for calculus was different from the Leibnizian differentials adopted later by continental mathematicians, Newton's geometric insights allowed him to anticipate many results that would eventually become standard in analysis. The ensuing controversy with Gottfried Wilhelm Leibniz further complicated the historical narrative of calculus's development. While Leibniz's notation eventually proved to be more convenient for capturing multivariate functions and integration on a broader scale, historical evidence confirms that Newton had mastered the essential techniques of fluxions well before Leibniz had even formulated his first ideas. Analytical reconstructions of Newton's manuscripts demonstrate how his method of first and last ratios encapsulated both differentiation and integration in a unified framework. In essence, his approach was both innovative and versatile, effectively handling problems ranging from motion under force to complex geometric constructions. Newton's contributions are richly detailed in his various manuscripts and personalized correspondence, which reveal an astonishing breadth of technical proficiency. His ability to transform abstract mathematical ideas into applicable computational techniques is evident in his careful treatment of infinite series and his groundbreaking development of what we now call calculus. Experts can appreciate the nuance in his methods, a blend of rigorous approximation techniques and intuitive understanding of limits that remains influential even in contemporary theoretical physics. The numerical precision with which he derived error estimates and his early use of what might be considered regression analysis for his experimental data set new standards of mathematical rigor. In summary, Newton's calculus innovations not only provided the tools needed to solve previously intractable problems, but they also offered a new perspective on the nature of continuous processes. The depth and resilience of his methods shed light on a recurring theme in applied mathematics: the power of geometric insight combined with analytic precision to unlock the secrets of the natural world. His seminal contributions continue to inspire modern research, ensuring that even centuries later, his methodologies remain a beacon for advanced studies in mathematics, physics, and engineering. Consequently, Newton's work not only advanced mathematical thought, but also foreshadowed the digital age, where numerical methods and computing algorithms are essential in solving real-world problems. To further contextualize Newton's contributions within the broader evolution of mathematical thought, it is crucial to recognize that his techniques were simultaneously revolutionary and deeply rooted in the traditions of classical geometry. His derivations, often relying on innovative limit processes, not only circumvented the need for the cumbersome method of exhaustion, but also anticipated the later formalizations seen in the 19th century rigorization of analysis. Newton's work on calculus provided a framework that elegantly blended the geometric intuitions of the ancients with the emerging analytic perspectives of his time. Detailed studies of his manuscripts reveal that his computations were underpinned by a robust attention to error analysis and convergence, characteristics that resonate strongly with modern numerical and analytical methods. Moreover, his interdisciplinary approach, merging insights from algebra, geometry, and physics, set a precedent for future generations of mathematicians and scientists to pursue bold, cross-disciplinary strategies in problem-solving. The methodological precision he exhibited is evident in his systematic exploration of differential equations and power series, techniques that remain integral to the ongoing refinement of computational models across various scientific domains. In total, these comprehensive innovations amount to an undisputed, enduring, monumental legacy in mathematical thought. Newton's pioneering experiments in optics constitute a tour de force that exposed the intrinsic properties of light in ways that challenged and ultimately redefined long-held paradigms. Utilizing prisms as both analytical and experimental tools, Newton demonstrated that white light is not a singular entity, but a composite of distinct spectral colors. In a masterful series of experiments conducted between 1666 and 1672, he systematically dispersed sunlight through a prism and then recombined its constituent colors to reconstitute white light, thereby refuting prevailing theories that posited light's purity. Through meticulous measurement and analysis, Newton quantified the angular dispersion of different wavelengths, thereby establishing the foundation for modern spectral analysis. His work revealed that each color refracts at a specific angle, a discovery that provided quantitative evidence for the relationship between wavelength and refractive index, an insight that remains central to contemporary optical physics. In an audacious display of experimental ingenuity, Newton developed the first reflecting telescope to overcome the problem of chromatic aberration inherent in refracting telescopes. With an innovative application of speculum metal as mirror material, he constructed an instrument that dramatically reduced optical distortions. This telescope, later known as the Newtonian telescope, served not only as a practical demonstration of reflective optics, but also as a catalyst for further explorations into the design of astronomical instruments. His precise measurements of the interference fringes, now called Newton's rings, employed a novel technique of averaging differences to minimize experimental error, paving the way for modern data reduction methodologies in optics and metrology. Newton's analytical approach extended well beyond simple demonstration. He introduced an early form of least squares regression by summing residuals to zero, compelling the experimental data to converge to an optimal line through the mean. This statistical treatment of optical data was unprecedented in the 17th century and presaged modern techniques in experimental physics. Detailed analysis of phenomena such as thin film interference, which Newton approached with a hybrid corpuscular wave perspective, underscored his recognition of dualistic behavior inherent to light. In his treatise Optics, Newton posed challenging queries that flirted with the modern concept of wave-particle duality, suggesting that light's behavior might be understood in terms yet to be discovered by future physicists. Moreover, Newton's optical experiments were underpinned by rigorous mathematical analysis and numerical precision. He developed methods to calculate the exact angular deviations produced by prisms and employed geometric constructions to predict the behavior of light beams interacting with multiple interfaces. His work involved an intricate interplay between empirical observation and theoretical modeling, as he used error-slaying techniques to refine his measurements of equinoxes and other astronomical events. Newton's experimentations were characterized by a systematic manipulation of variables and a commitment to reproducibility, aspects that established new benchmarks for scientific experimentation. Further examination of Newton's work in optics reveals a deep-rooted commitment to quantification. Modern spectral theory, laser technology, and beam expanders owe much to his early use of multiple prism configurations and dispersion models. His approach was not only experimental, but also computational, involving detailed calculations that would be recognized today as precursors to numerical analysis methods in physics. Each experiment was constructed with an appreciation for both the limitations and potential of the measuring instruments available at the time, and his distances and angles were determined with a precision that astonishes even today's engineers. In summary, Newton's optical discoveries represent an extraordinary fusion of creative experimentation and technical precision. His methods, replete with numerical detail and inventive procedures, have profoundly influenced the evolution of optical instrumentation and the theoretical considerations of light. The fusion of empirical observation with rigorous analytical methods in Newton's work laid the groundwork for modern optics, uniting concepts that are now central to fields such as photonics and quantum mechanics. These contributions continue to inspire not only technological innovation, but also deep theoretical inquiry into the very nature of light. Additionally, Newton's analytical measurements reflect a synthesis of mathematics with experimental physics, where each angular deviation and spectral measurement was recorded with extraordinary accuracy. His pioneering techniques in dispersive analysis not only enriched our understanding of light's behavior, but also provided a model for integrating quantitative rigor into experimental methodologies that underpin modern scientific research. These precise measurements remain influential standards in optical physics today. Newton's theory of gravity, as meticulously articulated in his magnum opus, the Principia Mathematica, represents one of the most profound achievements in scientific reasoning. As far back as 1665, Newton had set the intellectual foundations for his law of universal gravitation, which he refined through astronomical observations and theoretical insights. In 1679, following renewed engagement with celestial mechanics, sparked by the appearance of a comet, Newton began integrating his analytical methods with empirical data, thereby formulating the key principles that govern planetary motion. The Principia, published in 1687, with encouragement and financial assistance from Edmund Halley, crystallized Newton's ideas into a coherent formulation that has guided scientific inquiry for generations. Within this work, Newton laid out his three universal laws of motion, which described the intricate relationships between forces, mass, and acceleration. His articulation of the law of universal gravitation, which asserts that every mass attracts every other mass by a force proportional to the product of their masses and inversely proportional to the square of the distance between them, provided a numerical and conceptual underpinning for the motions of celestial bodies. Detailed geometric constructions and careful derivations in the Principia reveal Newton's innovative use of a calculus-like methodology to integrate differential equations, thereby allowing him to predict planetary paths, cometary orbits, and even the subtle precession of the equinoxes. Newton's treatment of the two-body and three-body problems exemplifies his deep engagement with complex dynamical systems. By formulating these problems in terms of centripetal forces and elliptical trajectories, he was able to derive relationships that remain valid even under modern perturbation analysis. His quantitative approach was not limited to celestial mechanics. He also estimated the speed of sound in air based on Boyle's law and inferred the oblateness of Earth due to its rotation. Each of these contributions was supported by rigorous mathematical derivations and a judicious application of experimental data. Newton's use of limiting values and infinitesimals in his geometrical methods bridged the gap between abstract mathematics and practical physics. Moreover, Newton's work on gravity prompted him to confront controversies surrounding the notion of occult forces. Critics of his time questioned the legitimacy of attributing gravitational effects to an unseen force acting at a distance. In his second edition of the Principia, Newton famously declared hypotheses non fingo, asserting that his primary concern was to describe the phenomena accurately without necessarily explaining the underlying cause. This pragmatic stance underscored the data-driven nature of his work, committing to mathematical precision while leaving the ultimate nature of gravity as an open question for future inquiry. Newton's gravitational theory not only unified the motions of heavenly bodies, but also established a paradigm for the application of mathematics in natural philosophy. His synthesis of geometric insight, analytical technique, and empirical rigor set the stage for subsequent developments in physics and astronomy, influencing disciplines from orbital mechanics to modern astrophysics. Today, the principles laid out in the Principia continue to serve as the foundational bedrock upon which classical dynamics is built, illustrating the enduring power of Newtonian mechanics in explaining both terrestrial and cosmic phenomena. Furthermore, Newton's analytical framework anticipated modern methods in perturbation theory and computational dynamics. His precise quantification of gravitational forces enabled the prediction of orbital perturbations and resonances observed in multi-body systems. Detailed error analysis, verified through astronomical observations, underscored his commitment to numerical rigor. His theoretical models, replete with intricate geometric proofs and series expansions, continue to offer valuable insights into nonlinear dynamics and celestial mechanics, forming a bridge between classical physics and modern computational simulations. This additional perspective reinforces the timeless applicability of Newton's gravitational models in advanced astrophysical research. Newton's monumental contributions have left an indelible mark on the scientific world, setting the stage for centuries of innovation. His rigorous methodologies and groundbreaking discoveries in calculus, optics, and gravity underpin much of modern science and engineering. The inventive techniques he pioneered, from fluxions to reflective telescopes, continue to propel contemporary research and inspire innovative computational models. His work has not only advanced theoretical understanding, but also practical applications in astronomy, physics, and technology. The meticulous blending of empirical data with geometric and analytical rigor in his research established a paradigm for scientific inquiry that endures today. By transforming abstract concepts into applied methodologies, Newton bridged the gap between pure mathematics and experimental science. Ultimately, his legacy is a testament to the power of intellectual curiosity and mathematical excellence, inviting experts to explore new frontiers built on a foundation of precise, data-driven insights. Newton's legacy endures as timeless scientific inspiration.